Hello everyone, in this video we are going to solve the fourth problem of INMO 2024 with the help of equivalence relation. So we last year also in INMO 2023, if you go and check, we also solved one of the problem with equivalence relation. Okay, so this is very important, and those who have studied sets and relations must be knowing about equivalence relations. And now let's come to the problem. So the fourth problem, so it's first defining some set which is cardinal. So basically it's a set where the number of numbers in the set, so that means whatever be the cardinality of the set, so that number should be present in that set. Okay, so then we will say that the set is cardinal, and then let f be a function from the set of positive integers. So from naturals to naturals, you are having a map f, which is basically doing the job, that is like it will take a cardinal set and map it to a cardinal set. So basically when it's taking cardinal set, so the image of that set, so we'll look at that set, and we'll see that whether it's cardinal or not. So that means like f is satisfying this relation. So now this is the problem, and now they are asking find all possible values of f 2024. Okay, so so let's get started. Okay, so what we'll do again, as I said, like first of all, let's briefly discuss the scenarios. So so you have the set of all natural numbers here and the set of all natural numbers here, because it has been told that f is a function from the set of positive integers to itself. Okay, so now try to understand that what is actually happening. So here I have 1 2 3 4 and so on. Okay, now here also I have 1 2 3 4 and so on. Now let's see where 1 can go and map to. So it can go and map to 1, but can it go and map to 2? Okay, or 3 or any other element. So now suppose if 1 goes and maps to 2, so that cannot happen, because 1, so that singleton set, so 1 as a singleton set, so that is a cardinal set. Okay, so then it has to go and map to a cardinal set. Now it can't go and map to two different elements simultaneously. So whatever its image is, it's a singleton set again. So that implies that it can't go and map to something other than 1, because 2 or 3 or 4 or any, like if n is greater than equals to 2, then the singleton set n is not cardinal, because if suppose n is 3, then the singleton set its cardinality is 1, and 1 is not present in that set, only 3 is there. So that's why it, so that means we are we can see that 1 will map to 1. Okay, in under such a map f. Okay, now what about the rest? So the rest, you can also similarly think where I mean what we can do. So there is one trivial map where what we can do is, like, since 1 as a singleton is cardinal, so we can map all the elements, the whole of this set, to just simply 1, like the constant map. Okay, so that will work as one of our map. So then trivially from that map we can see that like this map is working. Okay, it's satisfying the definition of f, and now the condition on f. Now as you can see, so we are getting that f of 2024 could be 1. That's a possibility. Now what are the other possibilities? Okay, so we can also see that if we take the identity map. Okay, so some trivial maps if we take, like one of them is the identity map, that is f of x is equals to x for all x belonging to n. So in this case also you can see that this is satisfying. Okay, that is it's satisfying the condition of f, and so you can also see that f of 2024 could be equals to 2024 as well. Okay, now also we can see something, that is, now try to understand that suppose if you want to make a cardinal set, okay, such a set with 3. Okay, so that means like with 3 will be there in that set, and you have and the cardinality of that set will also be 3, and uh, like there will be two or more elements, so you have to select two more elements. Okay, there can be other cardinal sets as well, but the easy construction would be like this. Okay, so try to think, that is, now if I have 3 in my if I want to make a cardinal set, okay, where I have the number 3 and the cardinality is also 3, so I'll put 3 and the rest 2 numbers. Okay, so the thing is that for 2, it's simply like if I want a cardinal set, okay, having cardinality 2, so 2 will be obviously there. Okay, and what we can do is, like, if we just with along with 2, if we also plug in 1, so like 1 comma 2, this is a cardinal set. Okay, and also now try to notice that, like, once I put in 2 in that set, I can also put some other values, like any n will also work, 3, 4 or 5. So I just have to keep some other number. Okay, so like 3. Okay, so that's what I was talking about. There are other cardinal sets having 3 as well, like this 2 comma 3. Okay, so but the main point is that, like I mean, if I want to have a cardinal set of cardinality 2, so I'll have to put the number 2 in it. Okay, so but that's by the definition. Now talking about here, that is, what if I just simply, like, if I have 2024 here, so what if I simply, like, map the rest till all of them to 1. Okay, till 2023 to 1, and 2024 goes and maps to 2. So the image is the whole of I have to also map the rest. So let's say that I'm also mapping the rest of the natural number. So let's say that except 2024, everyone is going to 1, and 2024 is going to 2. Okay, so this set, again, like, look at the image. Okay, so the image is again it's a cardinal set. Okay, but like, try to understand that 2024 as a singleton set, it's not cardinal. Okay, now whatever cardinal set you take now, okay, so if 2024 is there, so that set image will be 1 comma 2, which is cardinal. Okay, 2 is already there, and if 2024 is not there, so all those elements are going and mapping to 1, so then also it's cardinal, so it's satisfying. Okay, so that map is also satisfying the given condition of f, and so we have that f of 2024 could also be 2. Now the question remains is that, can there be any other possibilities? Okay, so now let's solve this with the help of our equivalence relation. Okay, so what we'll do is, we will so this set, on this set n, okay, we will define our equivalence relation. So try to understand that like, we have such a map f, okay, from n to n, and now we'll apply equivalence relation on the set of all positive integers, that is the natural numbers. Okay, and now I'm taking any arbitrary map which is which is satisfying such a condition given in the problem, and now I have to look where 2024 can go and map to. What are the all the possibilities? So now what I'm doing is, I'm defining my equivalence relation as, that is, like, x and y are related if and only if, so IFF means if and only if, let's say that f of x is equal to f of y. Okay, so where x and y belongs to the natural number set. So any two elements in the set of all positive integers, I'll say that they are related if they are mapping to the same number. Okay, so their image is the same. So basically, like, what is happening then, you can understand that for every element you pull back, so whatever be the set, you're getting. So that is basically like I mean all those elements are basically going to get related. Okay, so that means all those elements which are mapping to 1 are all related. Okay, all those elements which are mapping to 2 are all related, and so on and so forth. Now let's see that whether this relation is an equivalence relation or not. So what do we mean by an equivalence relation? Reflexive, transitive and symmetric. So the reflexive thing is very simple, like every element is related to itself because x is related to x. Why? Because f of x is equals to f of x, trivial. Okay, so now let's come to reflexive is done. So now what about symmetric? So x is related to y, is y related to x? So x is related to y implies that f of x is equals to f of y, and similarly, like then it also implies that f of y is equals to f of x, so y is related to x. So symmetric is also done. Now the other one is also trivial, like x is related to y and y is related to z. So now this implies what? This implies that f of x is equals to f of y, and this implies what? F of y is equals to f of z. Now, so from there you can get that f of x is equals to f of z, which implies that, like, see, this relation is if and only if. Okay, so the converse is also true. So f of x is equals to f of z, so which implies that x is related to z. Okay, so it's transitive as well. So this is an equivalence relation. Okay, fine. So now once we have an equivalence relation, so what I can do is, like, this whole set, okay, the set of all natural numbers. So suppose think that you have all the numbers here, and now what I can do is I can group them. Okay, so I can form the equivalence classes now. So how am I going to form the equivalence classes? So basically I'll group all those elements who are mapping to 1, okay, and then those who are mapping to 2, and so on. Okay, then those who are mapping to 3. Now it might be that none of them is mapping to 3, then that class will not exist. Okay, or I mean that will be empty basically. So now likewise I can continue on and divide this whole set of all natural numbers, this set, into equivalence classes. Okay, so now try to understand the advantage of this is that when you pick up two elements from two different classes, they are not related. So that means what? That is, they are mapping to two different elements. Okay, so and moreover you can also see, like, I am collecting here all those elements which are mapping to 2, and I am collecting here all those elements which are mapping to 3. So obviously if you pick up two elements from these two classes, so one is going to map to 2, another one is going to map to 3. So now the next big question is that like, will I have finitely many equivalence classes or infinitely many equivalence classes? So one would easily argue that since like I have infinitely many elements, 1 2 3 4 5 6, so goes on, so there can be infinitely many classes. Okay, but no, we claim that I'm claiming that there are finitely many classes. Okay, so why will there be finitely many classes? So let's go on the contrary. So on the contrary, let us think that so I'm not writing the claims. Okay, so I'm not writing everything, so I'm saying, so please try to understand what is happening. So my claim is that there will be finitely many classes. Okay, so how do I prove? So while you prove, you can write claim and so on and so forth, and then you're proving that. Okay, so how do we prove? On the contrary, what we can say is that no, let us have like I mean there are infinitely many classes. Okay, so then what do we get any contradiction? So we'll basically go with the help of contradiction. Okay, so now if there are infinitely many classes, so again one of the class will be like 2024 as well. So those elements which are going and mapping to 2024. So now I'll divide this into two cases. Okay, so the case where I have like case 1 where I have like f of 2024 is not equals to 2024. Okay, and case 2 will be f of 2024 is 2024. Okay, so now we have already like we now need to figure out that where all can 2024 get mapped to. Okay, so we have already seen in an example that yes, f of 2024 is equals to 2024 is possible. Okay, we saw in an example. So case 2 is very like we don't have to even verify, so we can already write the example. That is, we can just simply take all the elements to 1 and sorry, we can take simply the identity map, and in that case you are getting f of 2024 is equals to 2024. So that's a possibility, right? So now we are seeing that when f of 2024 is not equals to 2024, then what are the other possibilities? As we have seen that 1 and 2 are some of the possibilities. Okay, now is there any other possibility? So that we have to like verify. Okay, so now in this case where like 2024 is not getting mapped to 2024, so then we are like having, suppose we are having infinitely many classes. Okay, then there will be like what I am going to do is from like let's say like try to understand that there will be another class in which 2024 will be there present, right? So because 2024 is not going and mapping to 2024, so it won't be here, it would be in some other class. Okay, it's going and mapping to something, let's say it's mapping to k. Okay, so let's say that f of 2024 is going and mapping to k. So now what I'll do is I'll pick up numbers, like I'll pick up 2024 numbers. Okay, and let's say that like so I'll just avoid this class, the 2024 class. So that means all the elements who are going and mapping to 2024, I won't just consider that class. Okay, I have infinitely many classes, so still like one class I'm deleting, so still I have infinitely many classes. So now what I'll do is I'll just pick up 2023 classes. Okay, and along with that I'll pick up this class k, from where I'll pick up one element which is 2024. Okay, so try to understand again what I'm doing from this class. Since 2024 is there, I'm picking up 2024. Okay, I'm making my set, I'm picking up the 2024 element, and I'm making a set having 2024 elements, and the rest 2023 elements, and the rest 2023 elements are going to come from the, let's say the rest of the classes, like from every class, I'll just go with the class 1, and those elements who are mapping to 1, I'll just arbitrarily pick up one element. Okay, and likewise I'll go to the one of the next class and I'll pick up any arbitrary element, and so on. So since I have infinitely many classes, so I'll pick up, so this class I'm avoiding, and I have already picked up 2024 from this class. So next I won't pick up from these two classes. From the rest of the classes, I'll arbitrarily select 2023 classes, and from each of them I'll pick up one random element. Okay, so now it might happen that a class is also a singleton. Okay, so then I'll have to pick up that element which is present there. Okay, so now try to understand that this set, suppose this set is S. So S is cardinal because its cardinality is 2024. Okay, and also now try to understand that the image of F, that is image of S under F, which is f of S. Okay, f of S is a set. I'm looking at that is the image of S under the map F. So now try to understand that this will be like what? This will be f of 2024 will go to k, okay, and even the rest of the elements would go to some other number, and every one will go to some other number. They will map to some other number. Why? Because I have chosen those 2023 elements, each of them from different classes. So that's what in the beginning I said, that's the advantage. Like if I pick up an element from this class and this class, so they're not going to map it to the same element, okay. So this class, all the elements are mapping to 2, and this class, all the elements are mapping to 3. So since I picked up all those 2023 elements from different classes, so their images will be all different, okay, and thus I'll again have here 2023 different numbers, okay, so positive integers, and thus making my cardinality of f of s, this set, also 2024. But try to understand that since f of 2024 did not go to 2024 in our case, this case, so this set f of s should be cardinal, because s is cardinal. Under f, whatever the image of this set is, that should be cardinal, but this set is having cardinality 2024, but 2024 is not present inside that set. So a contradiction, and thus we now have proved that there will be finitely many equivalence classes, okay. So now there will be finitely many equivalence classes means what? I can divide the set of natural numbers into finitely many equivalence classes, means into finitely many groups, okay, like this. Try to imagine it like this, okay. So I have divided it into finitely many equivalence classes, but try to understand here, the set of all positive integers or the natural numbers, it's having infinitely many elements, right? So if I want to distribute infinitely many elements into finitely many boxes or whatever, into finitely many groups, then at least one of the groups should have infinitely many elements, right? So then the next question arises that which are the classes that can have infinitely many elements, okay. So, and try to understand that at least one of the class should be having infinitely many elements, because I have finitely many groups or classes, okay. So finitely many classes, if each of these classes are having finitely many elements, so the union of all of them will be finite, but the set of all positive integers is infinite. So coming down to the next question, that is which are the classes that will be like infinite, okay, cardinality will be infinite. So now try to understand that those elements which are mapping to 1, so that class is non-empty, because 1 will always, under such a map f, 1 will always map to 1, that we discussed in the beginning. So that is non-empty, okay. So now we also, in the beginning, we also saw here, that is, if I have like all the elements, if I just simply map to 1, so then that was also satisfying, okay. So we get an idea that yes, f of the equivalence class that of 1, that is all those elements which are going and mapping to 1, so that is cardinal, okay. So that is having infinitely many elements, okay. So that can have infinitely many elements, okay. But let's try to see that whether any other, let's say that this is n, okay. So this class is like presenting all those elements which are going and mapping to n, and let's take that n is greater than equals to 2, and let's say that, like, let's see that whether that class can have infinitely many elements or not, okay. So again, my claim here is that no, it can't. Okay, so now how do I prove it? I again go with the help of contradiction. That is, let's have infinitely many elements in that class. Okay, so in suppose there are infinitely many elements who has those who are mapped to n. Okay, where n is greater than equals to 2. So then where will the contradiction lie? So I have infinitely many elements, they are mapping to 2 or 3 or 4 or whatever. Okay, so I'm taking a particular n which is greater than equals to 2. So then how would I show the contradiction? Because I'm claiming that there are finitely many elements there. Okay, so now try to understand that simply, like, since there are infinitely many elements, you simply can like take try to understand that you can have a cardinal set there. Okay, you can make a cardinal set there. Okay, because like pick up any random element there, in that set, all those elements which are mapping to n. Okay, for example, let's take 3. Okay, so all those the elements which are mapping to 3. Okay, so what I'll do here is, that is, I'll pick up any random element present there. So I have like infinitely many elements in that class. So I'll pick up any random one of them out of them. Okay, so suppose that number is like, let's say, m. Okay, so f of m is equal to n. Okay, and let's say that like now try to understand that since there are infinitely many elements, I can take m elements out of it, right? M distinct elements. So I'll just form a set S1 which will have m and the rest m minus 1 elements. Okay, all these elements are coming from that equivalence class of n. That means all those elements which are mapping to n for Nagpur. So what happening is, like, the cardinality of the set S1 is m. Okay, so it's a cardinal set, but it should also map to a cardinal set. But then f of S1 is like only n. Okay, or if you take n to be 3, so it's only 3. So then n as a singleton set, as we discussed in the beginning, for n greater than equals to 2, it's not cardinal, thus giving a contradiction. And thus we can only see that, like, none of them, for n greater than equals to 2, so none of these classes can't be infinite. So that means only one class can be infinite, and it has to be, because I have to distribute all these infinitely many elements into finitely many boxes. So this is the infinite equivalence class having infinitely many elements. Okay, so then what? Then finally try to understand that, like, we now have to identify finally what's our objective, that where is f of 2024 going. Okay, so what we'll do is, like, since we have infinitely elements there, so I'll pick up randomly 2023 distinct elements from there, from the equivalence class of 1. Okay, so I'll pick up randomly 2023 elements like a1, a2, a20, 23. Okay, along with it I'll keep 2024. So now this set, suppose S2, this is cardinal, having 2024 elements, and all these f of ai's, they are going and mapping to 1. Okay, for I going from 1 to 20, 23. So they are all going and mapping to 1. And then what will be this f of S2? So this set will be 1 and wherever this f of 2024 is going and mapping to, right? So now try to understand that there could be like only two possibilities, because if this set has to be cardinal, okay, so then there are only two possibilities. That is, it becomes a singleton set and f of 2024 also goes to 1, or else if f of 2024 is going to some other element, okay, so then the cardinality of this set, like this image set, will be 2. So 2, if this has to be cardinal, the image has to be cardinal by the condition, so 2 has to be present there. So then, like, it has to be the set 1 comma 2, okay, which is also cardinal. So that means f of 2024 in this scenario can be either 1 or 2, okay, and this is case 1. And for case 2, if f of 2024 is 2024, then we have an example, like you have to also show with an example. So what you're saying is that, like, if f of 2024 is not equals to 2024, then f of 2024 can be 1 or 2, okay. But case 2, where you say that if f of 2024 is equal to 2024, then you have to also validate that case, that is possible under a map which does the job as described in the problem, okay. So as we have already showed that the identity map does the job. So for case 2, I'm not writing it down, so f of 2024 is equals to 2024, and again, as case 1 and case 2 exhaust all the possibilities of f of 2024, so we finally arrive at the conclusion that is f of 2024 can either be 1 or 2 or 2024. Yeah, and yeah, so that's it for this video. So I'll publish some more videos, and also we are basically like launching the workshop, and it's going to start this week. So the crash course for ISA CMI entrance exam for this year, and as well as the CMI data science crash course. And yeah, so if you're interested, you can contact us. And yeah, thanks for watching, and keep watching and keep learning, and see you in the next one.